So when you're looking at this question to kind of process through, what you're trying to figure out is what's missing from the beginning. So we do have the final answer, but what you have to acknowledge is more. You don't have just the final answer. You also have this information. What does that information look like? Okay, well, I have a CH3. I have two of them. Okay, they're both connected to a CH, connected to a CH2, connected to a Cl. That's all in formula speak, and formula speak is going to be a bit messy for us. So what we want to do is clean that up, and what I'm going to do is not only clean it up and get it into the line angle, because the line angle is more appropriate to what we've got here, but I'm also going to pick it up and I'm going to flip it. Okay, so I'm going to flip it. There's my chlorine. There's my CH2. There's my CH. That CH has those two pieces on it. Okay, so when we're talking about running this as a particular reaction, what I need to know is what's in that missing box. So what's missing up here. So I know this red thing exists. So let's find the red thing in the answer. So where's the red thing in the answer? And by the answer, I mean the product.
Right side. Without this.
It's right there. Okay? So when we're looking or considering what's in the box, oops, as I use the whole thing, okay, of what's in the box has to include everything that hasn't been highlighted by me in red. Okay? And so I'm making kind of this, all of this has to somehow be in there, and that this green bond connecting them is the new bond. Because the red part was already identified, that purple section needs to be new. Okay, so what I've got to do is figure out how to piece together these things, and we'll see if there's another active issue within this. So looking at that green bond, where would we expect those electrons to go naturally? To the oxygen. Okay, and the reason why we want to think about that is that means our oxygen should have electrons, aka be negative potentially in our answer, and that the carbon in our starting material should be positive. So if we now take that information and apply back to this, is that true?
Well, chlorine doesn't.
Is the chlorine on the structure anymore? No. What is the chlorine doing?
Leaving.
It is leaving by doing what? Taking these electrons with it. If it takes those electrons with it, what happens to that carbon? It becomes positively charged. Does that align with what we had down here?
Yes.
It does. Okay, so we're not doing anything fancy or tricky down there, which means the piece that we should be drawing in is what we've identified in purple. And I will struggle through it because I made you guys struggle through it. There's our oxygen, and then that oxygen, depending on how we need to worry about it, should have the lone pairs to be negatively charged. Okay, don't go entering it yet because I'll actually type that all in and see if it's coming up okay. Little bit questionable. It should be showing it as that, but I'll test it.
Into an OH.
Oh, so since we now have, God, we're okay with that, right? Mm-hmm. Okay, so since now we have that, I'll attempt to go through and draw. Oh, so we scroll through our system. We want our thing like that. No, jerk, come back. Can I do that? I want the negative oxygen. I don't see any lone pair electrons, but that should now be my structure. Can I submit? I guess I can't submit.
I tried it.
It doesn't want that?
It wants that. You have drawn a structure with an incorrect formal charge on one or more atoms.
It's not
I think it's just because there's
incorrect.
lone pairs there, and it won't let you put lone pairs.
So, and then this would be the next question that again I will pause for. things that I do want you doing is exactly this. I don't know how to do this question. Okay, let's talk through it. Let's talk through and let's see why we think there should be issues, how things should be adjusted, what should we be considering as we navigate these problems. That's important.
I figured it out, but I still want you to go over it.
One of the two diastereomers that are major products from this reaction. I will say in selecting questions, they had a bunch that were draw all the products, and I really tried to remove those, so I apologize if those snuck through. Because I don't want you drawing two of these structures. It's just not necessary. From this reaction, draw a dash or wedge to indicate the stereochemistry of the substituents on asymmetric centers. Ignore organic byproducts. This one actually has the potential to be really nasty, and I hope it's not. We'll see. Two approaches. Number one, this is also just a personal thing or beef with me. I feel the reagents are way too small, so it's hard to see those. I would try and draw them bigger so that you can see them. Once you've got it there and it's on roughly the same wavelength as the rest of the structure, we now get our two approaches. One, rote memorization. Did you memorize what happens when you see an alkene with BR2?
Yeah.
Ooh, dangerous. What did you memorize?
I memorized that the BRs go on each side of the alkene to break the pi bond.
Okay. So what you memorized is that alkene should place the bromine and the bromine, right?
Yeah, I didn't
Reference the
memorize
alkene.
the stereochemistry.
If we then address the rest of the structure, we still get that carbon. That carbon did nothing, so I should maintain that as a wedge. Okay. Now when I look at this answer, this becomes the problem with memorization. You have to know how much you need to memorize. What's the next layer that you have to worry about? We've drawn your product. What is special about this product?
That's multiple chiral atoms.
I would argue really we just care about those two chiral atoms. The one with the methyl did nothing in the overall chemistry, so who cares? Let's not worry about it. Okay, but what you do need to know is what's going on with those two bromines. Okay, did anybody memorize that next step further?
Something about anti versus syn.
What does that mean? What does syn mean?
They come in on the same side.
Okay, so what does anti mean?
They come in on opposite.
Okay, so what could we do?
Make them the same or different. I'm glad you did.
Fair point. You just said anti or syn. Which does this reaction do? Anti or syn? Did you memorize that, or are you guessing? Because we're now at 50-50.
I did not memorize it.
Okay, so if we don't memorize it, now we're kind of stuck in the water, which is why I don't like the memorization process, and instead I prefer to look at how the reaction works. So in the reaction working part, our electrons come out, attack the bromine. That exceeds the octet on the bromine, we'd have to have a leaving group. Do we have a good leaving group?
Yes.
Yes, so that would leave. Okay. What we're running is an electrophile addition. The process of this is breaking that pi bond and adding the positive bromine because the other bromine took our electrons. This one's coming off as a negative, the other one's positive. When we're looking at our electrophile additions, what we have to be concerned about is the two different mechanistic types. Do we have a good leaving group? And is the one that was attacked, does it have electrons to donate? It does. So what happens? Those donate back immediately. Okay. The resulting structure, didn't realize how much I actually liked having hexagons on the page, for the record, would give us that three-membered ring. That three-membered ring should scream all sorts of issues. First and foremost, it should scream that is a positive bromine. Okay. It should also scream that it is unstable and wants to break open. To break open, we would need a source of electrons, because what that bromine is going to do is steal electrons. Our black bromine is going to steal electrons from our carbon, okay, trying to break it open, thereby forming a positive charge on our carbon, which is why our negative bromide can come in and attack. Okay, what's that going to result in? That's going to result in the scenario that you memorized. The two bromines are added on either side of that carbon. Okay, but that ring structure should add another potential layer behind this. We have our chiral atoms already right now with this intermediate. Can I form that three-membered ring where one of those bonds is wedged and the other one is dashed?
No.
That is physically impossible. There is no three-dimensional way that you can make that triangle where one of those bonds is somehow down and connected to the same atom. That's not going to work. Okay? What does that mean? I can go through and I can show this being wedged or dashed. Remember, it said there's two products. Okay? If I show that as dashed, what happens to that methyl group?
Switch.
Sorry, I used the wrong language. The bromine I just showed was wedged. What happens to the methyl group?
Yeah.
That methyl becomes dashed. And we're talking about the methyl, it's the one that was where the bromine reacted. Does that make sense?
No.
So now what happens, our Br minus comes in and attacks. The connection to our black bromine is no longer there to the top. So if we were to color through, this is our black bromine in our product. What happened to that bond in this last step of the reaction?
It stayed wedged.
Nothing happened to it, which means it stays wedged. Okay? The other black bond broke. Okay? It broke because the Br minus came in from where?
The
The backside. What is the backside of a wedge?
dash.
A dash, which means that blue bromine needs to be dashed. If it is dashed, what becomes the methyl?
And that's anti.
Okay? To your words of anti versus syn. What they're referencing is when we look beginning to end. Okay, so what we've got is the mechanism all drawn up there. Can I delete all of the mechanism? Okay, so we erase all of that. Okay, when we're talking about anti versus syn, that BR is killing me being that small. What we're talking about is that when I run this reaction, I'm acknowledging that this is an addition reaction. I can also acknowledge that it's an electrophile addition. And when we run that addition, we get two options. We either get the two pieces that have been added across that pi bond, because remember addition is two sigma bonds. We either get them added on the same side or on opposite sides. If the process of doing that addition results on our new sigma bonds being same side, we call that a syn addition. Okay? If the new sigma bonds are on opposite sides, we call that anti. Okay? So that when we look beginning to end, what happened? We've got the two bromines that are added across the double bond. Those bromines are added on opposite sides, as noted by the wedges and dashes here. We would call that anti-addition. Okay? So if you wanted to memorize Br2 adds two bromines and it adds them as anti-addition, you now remove the mechanistic detail that's necessary to get to that answer. Does that make sense?
Every time there's a member ring, you're gonna get the anti.
Yes.
Okay. That's what
Yep. So understanding that syn and anti can come from looking at the mechanism. It can also come from just memorizing what the answer is. Okay? And if you haven't noted already, there's a reason why I don't just say what it is. It's because I literally have not memorized it in 20 plus years of doing this freaking chemistry. I have not bothered to memorize whether it was syn or anti. I run the reaction through my head and say, oh, those are added on opposite sides. So if you ever asked the question, is this an anti-reaction? Deer in the headlights for me, I don't know. And I'm going to have to sit there and think about it before I answer the question. Kind of, sort of? Okay. And then you would also get the opposite potential product. where the black bromine is dashed and the blue bromine is wedged.
And then that also makes the methyl on there dash.
That would also change the direction of the methyl. Yep. Make sense?
Yep.
Okay. Why is the other methyl up there? We'll call it the green one. Why is that one there?
Nothing happened to it, it doesn't change.
Nothing happened to it, nothing changed, so why show it? We're showing it here not for any particular insidious reason. In other cases, it would be insidious because we could say, what's the relationship between the products? And if all we're talking about is just an electrophile addition, the relationship between the products typically is an enantiomers. They're mirror images of each other. Okay? As long as we have another chiral atom in there that doesn't change, that changes the relationships, and they're now no longer enantiomers, they're diastereomers, because that one doesn't do the mirror image flip. Kind of, sort of. So that's kind of a next layer question. Homework, possibly. I don't think I would ask that on the exam. That's pushing some pretty deep thought. Make sense?
Yeah.
Other questions? In the active? Okay. I want to point out that this morning, last night, I think it was last night, I added in this last part doc. So if we look, for me personally, these are confusing to see. But we get the old review. Okay, so that was going through for exam 1 and 2, where I went through my reference and just created a whole bunch of multiple choice questions. Okay, and electrophile addition is covered within that. Okay, so everything is in that document. Last night I went through and did the last part, which is our nucleophile addition and EAS, electrophilic aromatic substitution, which we'll talk about either today or tomorrow. Today or Thursday. Okay. Last big announcement I'll point out. Actually, sorry, as I say that, I made sure that those two documents showed up in each of our 15 and 16 modules as well. So they're also down there. The Part 3 AI project, I haven't bothered to see if anybody's looked at that. It's just the discussion board. Fairly standard directions for a discussion board. Oh, there you go. Thanks, Nate. So post your summary about it, read everybody else's posts, and then as a way to kind of make sure that you've read them, what you need to do is find a post that aligns roughly with what your background was, whatever you were looking at, and then again use the AI program to tie what functional group you looked at back to theirs. If they did the same functional group, please don't do that. Tweak it somehow, switch to a different functional group. Does that make sense? Okay. But the idea is that this is trying to find, number one, that you can see where it connects in the real world, okay, and you can see how those functional groups are potentially interesting or relevant. Kind of make sense? Questions?
Can you change the due date for paper homework 6 to tomorrow or Friday? It's not
To
today.
tomorrow?
It's due today.
Oh, sure. And then there's paper homework 7,
Yeah.
which, again, theoretically, right, they aren't extra questions.
Yeah.
I just want to make sure everybody's aware of that. This isn't extra questions. It's use your active, use whatever work you're already pretty much doing.
Yep.
Okay. Getting people in other classes being like, I didn't know that. I'm like, oh, that fucking... what'd you say, Thursday?
You want Thursday?
Yeah, that works.
Okay.
6 is due then?
Yeah,
I did move it, right?
yeah.
Okay, then I won't check. Ooh, you said I think so.
Oh, can you also increase
Thursday.
the
Attempts.
tries on active 7?
7. intuitive. I mean,
I'm not guessing, I'm just confused.
no, it's fine. Greeting. There it is. When you've got things where you're drawing structures, I've had students go through literally infinite attempts to figure it out because there's multiple different ways that you can draw a structure and screw it up. So limiting your attempts for those is not particularly useful. It's hard to guess your way through drawing something. We looked at nucleophile addition. We just talked about the generics, though. We didn't actually get into the play posit. As I look at it, I think this is where we ended. So we talked about the generics for each of these, right? And by each of these, we modified it. Which, again, I think I did a decent job of the science. Whoops. Deleted all of those. I'm going to keep it deleted, but I'll talk about one of those in a second. And then I got rid of that one as well. Right, so we had those. Oop, and I got rid of Bear Vinegar. Yeah? Okay. I should not have deleted, well, Grignard's still there. I should not have deleted this cyanohydrin one. Sort of. And I'll address it kind of why in a second. The nitrogen ones and our oxygen ones become really important. Why did we say that those were important? Anybody remember?
Does they look confusing?
No, that's not why they're important, unfortunately. Nearly all of your biochemical pathways deal with those. Okay? So seeing the imines, this is our nitrogens, our imines, and our enamines show up incredibly frequently through almost all biochemical pathways. Okay? Do you need to know the chemistry of how those bonds shift around for your biochemistry class if you're going to take a biochemistry class? Probably not, though it does depend on your biochemistry instructor. Somebody had to take biochem, right? Was it just you?
I'm sure I do, but I'm
You
sure
do?
others do.
Okay. What you will likely find is that the pool of students going into biochem is so odd that the instructors make massive concessions and they effectively remove all chemistry from it and it just becomes a biology class. Okay? And in that context, you don't need to know the structures or how those things are happening. You just need to know that they happen and you just know the answers. So it becomes just a test on memorization, which is somewhat unfortunate that I recorded, but I'm pretty sure no one's going to debate that. Okay? When we go through and look at our oxygens, okay, the real big one is what's addressed here, really down here and here. We've got the hemi, as in halfway, and then the bottom are full acetal. Those are important because that's carbohydrate chemistry. So when you take a biochemistry class, if you take a biochemistry class and you talk anything about carbohydrates, they are all oscillating through acetals and hemiacetals depending on what state they're in and what they're being used for. Okay? On top of which, when you reference those carbohydrates, you're referencing six-membered rings. And how do we draw six-membered rings? What was that? Yeah, we draw it as chairs. So when you draw it as chairs, you can get an idea of the energetics of that system. And again, whether that's addressed in a biochemistry class or not, I don't know. But that is why certain glucose molecules function as carbohydrates and energy, and other glucose molecules function as cellular structure. okay, because of the chairs and how those things are formed. Okay, and we'll look a little bit at them, but we officially already looked at them when we looked at chairs. Okay. Last one, I should have looked at or kept this pathway on here, ultimately down to this one. Okay, and the reason being has to do with the ability to exchange that OH for a nitrogen, because it's not too challenging a chemistry to go through and do that. Okay, and if I turn that into a nitrogen, why would this pathway be particularly relevant to us? It is officially a nitration, so if you've heard of transaminations or things like that in a biochemistry class or maybe even a nutrition class, we are technically changing the nitrogen around, and you could hear chemistry referencing that. Not directly why it's important here. What functional group was that?
So amino. Or amino.
What functional group is the bottom one?
So carboxylic acid.
Carboxylic what?
Acid, so it's amino acid.
This pathway is incredibly important for anybody trying to do synthetic biochemistry. So if you're looking at an organic joining a field where they were trying to make individual proteins, this would be a pathway that we could make amino acids that we could then potentially use to synthesize other things. Okay. It has some massive limitations and repercussions, and we have much better chemistry to address it, but it at least brings in that functional group characteristics that you could see where it's coming from and how we could potentially do that from a synthetic point of view. Kind of, sort of? Okay. Didn't want to do that. So, what? Didn't want to do that either. What I did want to do is focus a little bit on this middle section, because I would probably bet, I haven't looked to see if everybody's done it, the acetal video that you watched was probably a bit overwhelming. Okay. It is one that I was on the fence on including, because that video in particular receives the most complaints from students. And I haven't taught this class, that's complaints from people in second semester organic chemistry, so they've had significantly more chemistry than you have had. So the levels of questions that are getting asked in the content delivery is not the greatest, and it's one that I need to rework, though I'm not sure how to, which is why it hasn't been done. Okay, what we're talking about here is how we convert a carbonyl down into the acetal. So if we're addressing our chemistry, okay, we've got a polar pi bond. That polar pi bond maintains kind of the chemistry, because in our carbonyl, what we've got is two bonds to oxygen. Just one of them is sigma and one of them is pi. If we look at the acetal, we still have two bonds to oxygen. Okay, they're different oxygens though. Okay, so it's the same kind of core chemistry, but we've limited some of it. Okay, and one of the big things or synthetic reasons why we would do that is that polar pi bonds react very, very specifically. They react because of that higher energy pi bond. We get nucleophiles coming in and attacking. Right? If we go through and look at the acetal, what happens to the polar pi bond? Said another way, do you see a polar pi bond in the acetal? No, it's gone. Okay? So what we could do is we can make acetals to hide the chemistry of the carbonyl. Okay? When we make carbonyls react with nucleophiles, can a nucleophile easily react with the acetal? It's a harder question. N or NUC for nucleophile, what's the characteristic? What other thing could I draw on top of this to represent my nucleophile? Lone pairs. Okay, what do I need that nucleophile to find?
A positive.
Is there a positive in my acetal?
There's
Partial positive where?
the two carbons. Or technically, yeah.
that middle carbon is going to be by far the most positive within that molecule. It's got two electronegative, second most electronegative element, okay, connected to it. That carbon's going to be exceptionally positive. Okay? Could I have the electrons come in and attack? Why not? Okay? Exceeded octet, not a bad idea, but then I would need to kick out a leaving group. Is oxygen electronegative enough to withdraw electrons?
Yeah.
Okay. Can I run this?
Yeah.
Okay, we might say, yeah. What kind of reaction are we showing here?
Substitution.
Cool. Substitution. What kind of mechanism?
I need to rememorize my mechanisms.
Right? This is one, and not to be too salty on it, but it's definitely going to come out that way, that you should know, because this isn't just general, what were all the mechanistic steps. We spent 3 weeks looking at this particular mechanism. What was that? Did you say something? Who said it?
Is it a SN2?
Yeah, it's SN2. This is all happening in one fell swoop. Okay? At least how we've got it drawn. Okay, so we're looking at an SN2 reaction. Is that likely? When I say SN2, you say backside attack. What's on the backside of that leaving group? What are 1 and 2? Carbons. What is that? Oxygen. How many electrons are on the backside? A lot. There's a lot of electrons on that backside, which means the ability for that nucleophile to come in and do a backside attack is very, very limited. Okay? Up here, a nucleophile attacks immediately. We're reacting with a polar pi bond phenomenally easily. Down here, there's this now massive steric consideration that minimizes the ability for that nucleophile attack. Okay? Effectively negating that. That's one of the reasons why converting it into an acetal becomes very powerful, is we limit the ability to run that secondary reaction or another reaction. Why is that useful? Everything that we've talked about is the primary functional group. But if we think to our larger structures, there's almost always going to be something else out here. That something else could get in the way. That something else could be where I want to do the chemistry. I want to do a substitution out here. And if I throw a nucleophile in, the nucleophile is going to react with the carbonyl, not with what I'm trying to react with out there. So what I would do is try and create systems that prevent access to certain functionalities. Acetals get this name of protecting groups because they protect, they hide the carbonyl chemistry. Okay? Why are they particularly interest to us? When we talk about biochemistry, well, when we talk about biochem, we could look at, does anybody know the structure of glucose? Like if I draw it wrong, you all point and laugh?
No.
Okay,
not
cool.
yet.
Good. So I'll butcher it. Under the assumption that you never quote this to anybody. 1, 2, 3, 4, 5, 6. I think I got it. Oops. And then these other bonds are hydrogens. I might be right. I honestly don't know. Right? So that when we go through and look at glucose in our straight chain format, what do we have screaming at the top? A carbonyl. That's now susceptible to nucleophilic attack. Okay? Nucleophiles, like anything that would donate electrons. Well, what is our body made up of? 70% of? Water. And what does water have? Water is H2O, but it also has lone pair electrons, meaning it could act as a nucleophile and potentially react and change this chemistry out. Okay? So these particular, or all carbohydrates, have picked up kind of this self-preservation system to kind of hide that chemistry. And we go through 1, 2, 3, 4, 5, 6. And we would take the electrons from our oxygen and it would react back at that carbonyl. Okay? That ejects the pi bond, and what we end up forming is a hemiacetal, at least initially. And if we were to try and draw this all out, I'm going to butcher it. We would get a 6-membered ring 1, 2, 3, 4, 5, and then the oxygen is 6. So I'd have my oxygen in there. And then we could go through and look at each of the individual positions. Okay, I'm going to call this position 1, and that's going to be important for us. Okay, the rest of our structure, if we're going to draw this as a Hayworth, I'm pretty sure I screwed this formula up for glucose. Oh well. Okay, we could draw in the rest of our systems representing kind of the up-down stereochemistry. Kind of, sort of. Okay. Position 1 is then where we would have that last oxygen, okay, coming out. But hopefully what we notice is there's a little bit of an issue with where that chemistry happened at position 1. What have we just generated? That's another stereo center. Okay? And as a stereo center, how that 6 oxygen came back and attacked. Did it attack the carbon from the top side of the pi system or from the back side? Okay? And by backside, I mean top of our p orbitals or from the other side p orbitals. It's equal access. Okay? But depending on how it comes in is going to change the orientation of this alcohol. We could get that OH, or forming OH being down, or we could get that forming OH being up, depending on how oxygen 6 came in and attacked. Okay? What this is referring to, biochemistry throws in a name, epimers. Anybody know? Is that right? No? Okay, I don't remember. I think it's epimers, maybe apomers, apogees. Okay, have you ever seen that? Brune candlesticks and broom handles, whatever. Okay. And our oxygen can either be up or down. Because we get those two options, we go through and name them, and you'll hear reference to alpha and beta glucose. Have you heard reference to alpha and beta glucose?
Yeah.
Okay, cool. Why do we call them alpha and beta glucose? There's 2 possible outcomes. Okay. Interestingly enough, I haven't looked into it, but I think it's actually fairly true. We discovered alpha glucose first. Okay, why did we discover alpha glucose first? If we convert our glucose molecule into a chair, what you will find is that alpha glucose is higher in energy. Because it is higher in energy, what does that mean? It's more reactive. Why did we find it first? More reactive. It was easier to identify. Beta glucose came along later. We're like, oh, well, crap, there's a different one. So now we've got to name them both. So we'll call them alpha and beta because there were 2 forms. We'll call them 1 and 2 effectively. There's alpha, beta. Beta is now the more stable chair configuration for our glucose molecule. Why did we not discover it? Because it was more stable. Okay? Why did we not discover it even further? It was more stable and used as cellular structure, effectively making it non-reactive in all of our systems. So plants, animals, enzymes don't break it down because it's supposed to make cellular structure. And if it's so kind of strong and rigid, we never can actually access it to discover it. And it takes time to then process through that. So we get those 2 configurations. You get your alpha and your beta, and then you can reference all the D's and L's and all sorts of other nonsense that comes along with our carbohydrate chemistry. Okay? But because that chemistry is present, that's why it's important to address our acetal chemistry. Kind of, sort of? So when we talk about that interconversion, you're starting at the carbonyl and you're now reacting it with an alcohol. There are 2 potential alcohol forms that you can run through. Because when we looked at our carbonyl, we had multiple chemistries, right? What were the multiple chemistries of our carbonyl? Yes, the resonance structure drew attention to that chemistry. What were the chemistries? I had a negative oxygen and a positive carbon, which means if I run this under basic conditions, I'm taking a negative oxygen. What's that negative oxygen going to do? It's going to go to the positive carbon. Or I could run it under acidic conditions, and what is my hydrogen going to do? Go to that negative oxygen. Okay? So what we're talking about is how those individual species go through and stepwise through each of those reactions. Kind of, sort of. The point of that video was to kind of theoretically slowly approach how you could go through and crank through those systems, and then looking at that gloriously huge, massive mechanism. Okay? The more important pathway to be aware of is the acid pathway, because of the last step. Going from the hemiacetal to the acetal only runs under acidic conditions. Why not? For the exact same reason we had problems down here. We run into steric issues if we try to run under base conditions. Okay? Under acid conditions, we generate good leaving groups. The leaving groups leave. We have stable carbocations. That's what facilitates the rest of that reaction. Kind of, sort of? So that when we advance quickly through all those slides, what we're trying to do is, again, address that background. What are the basic kind of tenets behind each of those? We see this stuff about equilibrium. I know that's kind of frustrating and outside of your realm of experience. Don't stress about the equilibrium part, but it does become an important thing because it allows this reaction to be reversible. When I make that carbohydrate ring, I want to be able to revert it back to the straight chain, because the straight chain is now more reactive and I can now start to process it. Why would I process it? Every time I break one of those bonds, what have I released? Energy. That's how we live. And we convert each of those carbons into carbon dioxide. So we need a place to store it and to be able to react it. So we have to be able to oscillate back and forth between those both systems. That's why we're talking about equilibrium. Okay? The video starts with it looking at just water. Water goes through and forms the hydrate. It's not all that exciting, but we could go through and do it with water. The more relevant one is when you shift to an alcohol, because the alcohol is now where you're actually moving into that acetal formation. In this configuration, it looks like those two things are separate. Okay? And this becomes one of the challenging things within OChem. The chemistry is the carbonyl and the OH. I don't care what that R group is. That R group could very easily be connected across. The only limitation on it is that that chain is long enough that it can physically loop back. That's it. Okay? This is why glucose is so common, because what does it form when it loops back? 6-membered rings. And why are 6-membered rings special? They're the lowest energy ring. That's why glucose is 6-membered, because it's the most stable ring structure that we can get. All the other ones aren't easy to go through and form, so we don't see them as commonly. Okay? Are there other rings that show up? What's another common carbohydrate other than glucose? Cellulose is a string of glucoses. I could be wrong. Fructose?
Yes.
Yeah.
Sucrose, fructose.
And fructose is a 5-membered ring? Did I get that one right? No one knows that. There's fructose, sucrose, glucose, and yeah. I think fructose is the 5-membered ring. Okay? And depending on how you then link them to different carbohydrates, you get your different sugar sources. Okay? So what this is trying to get you to do is to slowly kind of move through and see each of those kind of pieces. So we're starting with our carbonyl. Under acidic conditions, we protonate. Okay? Once it's protonated, that carbon now becomes uber electrophilic because the oxygen doesn't want to become positive or be positive, so it steals the electrons even harder, which is why our oxygen can come in and attack. Okay? So what we're doing is stringing these things along with each other. Ideally, perfect world, you would know all this mechanism stuff. Okay? And that response is absolutely 100% fair. I know nobody else saw it, but there was a wide-eyed like, oh my God, you're full of shit. Okay? I can appreciate that. But that's the ideal scenario. Okay? Minimally, what you need to be able to recognize is how they're related. Carbonyls convert to hemiacetals. Hemiacetals convert to acetals. Okay? And I can flip that and go the other direction. Okay? Deciding how to direct where to go has to do with some of our secondary pieces. If I'm at the carbonyl and I want to make the acetal, I need the OR. Right? If I'm at the acetal and I want to get to the carbonyl, I need water. So it's recognizing how these things step through. So if we were to color code, that alcohol is our OR, is our OR, is our OR. The water is the OH, is the carbonyl. That's where those pieces are coming from and where they're going to. How do we know all that? That's the gory detail of that mechanism. Right? And if you look at that mechanism and go, oh, that's way too long, that's horrendous, everybody does. Right? But stepwise through, look at each of those steps and acknowledge, really, is it that much of a challenge? What's that very first step? What happened up here? What did you do?
Protonated the oxygen.
You mean you did an acid-base reaction? Acid-base, that's really that hard. You can't do an acid-base reaction. I think you can. Okay, what's the next step? Bringing in the nucleophile. What is that nucleophile doing? SN2 would just be the loss of a leaving group. What was the leaving group? What left the molecule? Nothing left the molecule. What else changed as we look at the next step? We lost a pi bond. What reaction results in the loss of a pi bond? Our addition. Is that one challenge? Yes, absolutely, hands down. Yes, that's absolutely challenging. I grant you that one. What's happening in the next step?
Loss of hydrogen.
Okay. Said another way.
Acid base.
Acid base. Do you have enough experience to understand acid base? Yeah. So the 3 steps, you have 2 of them are acid base. Right? What's happening in the next one? Down here. Acid base. What's happening in the next one? It isn't a substitution because nothing replaced that carbon. Not until the next step. That's the leaving group leaving. If the leaving group just leaves, if we just break a bond, that's called heterolysis. Is that a harder one? Yeah. I'll grant you that. Okay, what's the next one? That one's coordination. Why do you keep saying substitution? What reaction combines heterolysis and coordination?
I don't want to say it again.
It's an SN1 mechanism. Okay, what's happening in the last step? Acid base. So within all of that gory detail of all the arrows flying and everything moving around, really I would say, one, you've got very small experience with, and then the heterolysis coordination, you may not have known well, but you recognize the patterns behind what was going on with that. That was good. You were acknowledging the substitution. Okay, relatively straightforward as well. We've had a lot more experience with that. So within 1, 2, 3, 4, 5, 6, 7 steps, you have trouble with one and you're going to throw the whole thing out? That's not nice. Okay? So chunk things. Break it into smaller pieces so that you can see what those things are doing. Add charges. Slowly move through. I don't like that charge. Fix that charge. That allows you to navigate through these things much better than just rote memorization, because the rote memorization, guarantee you will forget within minutes of the final exam. But ideally what I've set you up with is the ability to recognize those patterns on how those things can react that you could apply into a future situation. Okay? And for those people, I won't remember any of those names. Even if you just memorized, you went through a different class where all you did was just memorize things, you weren't going to remember the names then either. Okay? What should be sticking with you are how those things react and how they interact with each other. And it's how we take advantage of those things that pushes both organic chemistry or biochemistry or dietetics. that right? Dietetics?
No, I thought it was.
Dietetics? Oh, it is? Okay, cool. Just because I knew a couple people were in that. Okay? Because you're looking at how those things interact with each other. Will you use it on a day-to-day basis? No, that's not the point. The point is recognizing how do you build these structures to see how they interact. And by build these structures, it's the thought process that you're trying to pick up, not the actual fact. Kind of, sort of? Okay. This is getting into that equilibrium stuff again, beyond the scope. There's only so much I can do to edit videos after the fact and limit things. Okay? Which then pushes us into nucleophile addition and elimination. If we look at what we ran in the previous reactions, on the previous slides, we just looked at a carbonyl and we said effectively that we ignored what those question marks were. We just made them carbons or hydrogens. Okay? So when we looked at the chemistry of this, what happens? Okay, well, we see the positive on our carbon, we see the negative potentially building on our oxygen, and that's really the end of it. We don't really do anything beyond that. Okay? If a nucleophile comes in and reacts, as we might expect, we can predict a product, and because we've been vague about what's happening at those ends, we get the nucleophile connected, we get the oxygen with a formal negative charge, we can stabilize that negative oxygen by giving it a hydrogen, and we're done. Kind of, sort of? Okay. Well, that's all fine and well until we move into this next unit where now we add some specificity. Instead of saying we were looking at carbons or hydrogens on either end, we go through and we use this fancy terminology, LG, which should look familiar. We've seen that before. What is LG? A leaving group. Okay. Why could the carbon not act as a leaving group? That carbon can't stabilize the negative charge well, so it can't act as a leaving group. But what happens if I make that a halogen? Now it can. Does that change the reaction? Okay. We're still going to see the primary functional group is our carbonyl, the primary chemistry. But if I now have, say, a chlorine there, where else could that oxygen as a negative find a positive? It could crash those electrons back down towards that middle carbon. That middle carbon is now happy, has its octet. In fact, it's over happy. It has too many electrons. So what could we do? We could kick out the chloride. The result is that I reform the carbonyl, and I now have this nucleophile, and then I've got chloride chilling off on its own. Okay? We didn't see that before because the atom that we had placed there was incapable of stabilizing the electrons. How does it change if it is capable? Well, it changes with secondary chemistry. The primary chemistry stays exactly the same. We're still doing a nucleophile addition. But what ends up happening is we get this particular chemistry that is now potentially problematic. Okay? That carbon becomes a little bit more reactive when I have a leaving group on it. Well, what is a leaving? What's the general characteristic of a leaving group? It's electronegative. So what's extra special about that carbon? It has two electronegative elements connected to it. That means it's unstable, and it's trying to stabilize somehow. That should look kind of familiar. What that should kind of look like, let's find one where it's not so busy. Can't do much about it. Okay, let's look at the acetal. What does the acetal have connected to it? And two electronegative elements. Was it particularly stable? No, that was a reversible reaction. Okay? We get effectively the same thing in our in the next kind of unit, if we will, or our next type of reaction. are nucleophile addition eliminations. We're generating a carbon with two very electronegative elements connected to it. It doesn't like that, and it tries to fix that by attracting electrons from one of those sources. Okay? What that's invariably going to do is result in the formation or the reformation of our carbonyl and an ejection of a new leaving group. When does this reaction actually function? How do I know it should do this? Okay? Said another way, the old chemistry was that that was a carbon. That was a carbon. That was a carbon. When it was a carbon, did this reaction work? No, it stalled, right? It stalled right here and it stopped. And it went a different path. Why is it allowed to continue this way? Why does the leaving group matter? What makes it good? Stability. Stability in comparison to what? What was one of the nucleophiles we used? Br2 was not a nucleophile. Br2 was an electrophile. Say it again?
Bromine, iodine.
We didn't use bromine or iodine, okay, which is a common one. So what's happening there is you're working through active, okay, and we're behind when we look at lecture versus active. Active is looking at electrophile addition. When we look at bromine, we go, oh, bromine has bromide. Bromine does not have bromide. Bromine has Br2. Bromine is electronegative, withdrawing those electrons. I don't have Br minus yet. To get Br minus, what has to happen? Those electrons must break, and I would get two things. Yes, I get Br minus, but what else do I get? Br positive. Which of those two is the reactive one? Why the positive?
Bromine doesn't like to be positive?
Do better. That's not horrible, but do better. That's going back to that. What was that? Octet. Okay, we go all the way back to the very beginning. Okay, bromine wants an octet. Okay, all of our atoms need an octet. So if this polarization is going to happen, yes, it gets me Br minus, but it also nets me Br positive. And between those two, which one's more reactive? The Br positive, because it's missing an octet. Okay, so I know you want to see Br minus, and it's great you're seeing a negative. It ain't negative until the bond breaks. Once the bond breaks, the positive is the one that you got to worry about. Okay, so bromine, iodine, chlorine, all in their elemental states are not nucleophiles. They are electrophiles. If you want to make them a nucleophile, we can do that. Let's just say Br minus. Did we talk about Br minus as a nucleophile? With these polar pi bonds? No. Why not?
Really big?
Why didn't I ever say Br minus can come in because it's negative, tack as a nucleophile and do that? Why is that something we never talked about? Oh, okay, it doesn't happen. It's a bit of a cop-out. Why does it not happen? Big isn't quite good enough. Electronegativity isn't quite good enough. Would I expect this reaction to occur? Is that a good thing? Why is that a good thing? We look at charge on the left, we look at charge on the right, and they are different, where this one's neutral and that one's charged. This makes a lot of sense to react because I neutralize the charge. What's the charge over here? Br minus. What's the charge over here? It's not neutral, a negative oxygen.
Oh.
Which one stabilizes the charge better? Why does bromine stabilize the charge better than oxygen? Now you can say size. So when we're looking at that chemical reaction, deciding whether it happens is a comparison between the most reactive thing on both sides of the equation. Saying bromide is large, yeah, but why do I care? Okay? Because I could put bromide here as large and yet it works. Why did it work here? It neutralizes the charge. This reaction doesn't work because I'm comparing negative bromide to negative oxygen. Bromide stabilizes the charge much better than the oxygen, which means, bromide, no, I'm not going to react. I'm going to make something higher in energy. That's bad. Okay? So was bromide one of the nucleophiles we looked at? No, because it creates something that's more reactive than where we started. Okay, so if bromide wasn't a nucleophile, what was a different nucleophile?
OH minus.
Okay, we could look at OH minus. Does this reaction work? Yeah. Okay, and if you're questioning that, that's literally our hemiacetal pathway. Okay, that's our hydrate pathway that we just cursorily jumped all over. Okay, so yes, that works. What other nucleophiles?
That's a no.
Water. What's the nucleophile in water? Oxygen. What's the nucleophile in a negative oxygen? Still oxygen. So I would argue you have not given me a new nucleophile. You gave me the exact same one in a different form. What other nucleophiles did we use? We used H minus. Okay, that was our borohydride. We used N when we're looking at our imines and our enamines. Again, reviewed real quickly today. When did it stop recording? That was the name Grignard. Okay. Why did all of those work? Because when I compare them all to O minus, they are all less stable than O minus, which is why that reaction cascades. Why would I ever go through and have the next step of this reaction work? What is the necessary repercussion that has to happen? Whatever that leaving group is, needs to be ish, closer, more stable than the negative oxygen. Okay? So what I'm backtracking through is now what are all the possible things that I could have as leaving groups? I could have oxygens as leaving groups. Okay? Because that's now oxygen versus oxygen. Is that going to be a great reaction? No, because they're roughly the same stability. Okay? But that would work. Okay? I could have chlorines. Ooh, chlorine's much more stable. So that reaction would work really well. Okay? And what you're processing through is now effectively all of these secondary chunks. Okay? And hopefully what you notice within these is right here, there's our oxygen. Okay? We go above, you'd be like, but isn't that also oxygen? That's actually a step beyond just an oxygen. Why is this one a step beyond an oxygen?
Add a whole another carbon.
Why does that matter?
Then that carbonyl could react.
Remember, it was all about leaving group ability, and leaving group ability has to do with the stability of the thing that's leaving. That's negative oxygen. Is that just the same negative oxygen as that? No, why not? It has resonance stabilization. That's why it shifts up on this ladder. What's the ladder? Chlorine, because more stable than the oxygen. Note the nitrogen is lower than it. Why is the nitrogen lower?
It's less stable.
Why would it be less stable? What can the nitrogen do better than the oxygen? right idea, wrong words. The nitrogen is lower in electronegativity, meaning it is more able to share the electrons inwards. Okay? So that if we were going to compare our leaving group's abilities, we're going to start to lose some chemistry there. We drop all the way down to here with it O minus, and that's all the way at the bottom. What happens there? If that left, what would I get? Extra O minus 2. That's horrendous. That's horrible. That would never happen. Exactly right. Okay? And so what we're providing within this kind of section is what are potential leaving groups. Okay? These all happen to be leaving groups that are common. Okay? The upper ones are more active than our straight oxygen as a leaving group, and therefore are more likely to occur all the way across. The ones lower than the oxygen are less likely to occur because they stabilize better. Okay? This is where we could throw in our carbons, our hydrogens, and other things like that. So what we're evaluating is the stability of each of those pieces and how they propagate through each of those kind of connections. Kind of, sort of? Okay? So the big piece to kind of get out of here would be, note it's a repeat of that system. What this is trying to reference is effectively a reactivity ladder. Okay? This functional group, our carbonyl with chlorine on it, is an incredibly reactive species. Okay? Phenomenal leaving group. That's making this carbon super positive, which means it's extremely electrophilic. The next piece underneath it has a resonance stabilization, but it's still oxygen versus chlorine. And since chlorine is larger, stabilizes the charge better. So what you're trying to get out of it is what are those relative energies of those systems, because those relative energies are going to predict whether you can react or not react. Okay? The next part that you're seeing connected on it are, of course, reaction arrows. Note, there's lots of arrows going down. I can go from the acyl chloride down to this one. I can go down to the next one. I can go down to the next one. So I can go down the ladder really easily. Going up is a little bit harder. Okay? You'll note, even here on the right, this arrow is saying down. How do I go up? There's only one. Highlander. Okay? I can only go from the carboxylic acid up to the acyl chloride. I cannot go from the acid up to here. Doesn't work. Okay? So I need a very particular reagent to force that chemistry to go upwards. Okay? That's kind of neat. And so a large part of what would happen in a normal class would be that you'd look at each and every single one of those mechanisms, talk about each of the charges in between each of those things. What, again, I want you to recognize is the patterns behind those and the relative reactivity staircase behind them. Kind of, sort of? I do want to draw attention to some important ones. Number one, why might we point out the carboxylic acid? Why do I care about acids? What were proteins made up of? Amino acids. You're going to see that show up in all of your protein chemistry as the carboxylic acid functional group. And you will see how that acid functional group can react with other functional groups. So it's really important to know what that acid can go through and do. Okay? The other one that I would argue is really important to know would be this guy. Okay? That one becomes a little bit harder to identify because the functional group we're looking at there is an amide. Well, how do you get an amide? Okay? We could take the acid and we could react it with that functional group. What is that thing in red? An amine. Why would I be concerned about looking at an amide? What happens when I take an acid and I react it with an amine? I get an amide bond. Where might I be concerned about acids and amines? Amino acids. When I take one amino acid and I react it with another amino acid, they connect to form an amide. The entire backbone of all of your proteins are amide linkages. Okay? So being aware of the connectivity or the reactivity between those becomes relevant for anything that you would look at, again, within biochemistry relative to proteins. Okay? Kind of, sort of? Okay. So we could go through and look at the exact same system that we did with our normal carbonyl. So we could start with our hydride nucleophiles. What is a hydride nucleophile going to do? So sodium BH4, hopefully we can memorize, is H-. What does the nucleophile do? Reacts with the carbonyl, breaks the pi bond. Okay, that's the old chemistry. Now what can happen? Cl can't leave on its own. It's forced off by the oxygen sharing electrons back down and kicking it out. What do we produce? Hydrogen's in place of the Cl, so it would look like effectively a substitution. Would we be done? It's a hard question. Because you asked it, Mike. No. Okay. What functional group did we produce? That is not a ketone. I accept that. It's its partner. Instead of a ketone, it's an aldehyde. How do aldehydes react in the presence of sodium borohydride? What happens in these particular scenarios? The reaction is going to run twice. The product that we produce reacts with the reagent just like our starting material. So one of the added complications that we're going to encounter, particularly with our strong nucleophiles, our negative hydrogens and our negative carbons, is they're going to continue to react. Okay? They don't run once, they run twice. Okay? Our ketones react with sodium borohydride. Officially, we didn't draw a ketone down here, but what happens is we formed its partner compound, the aldehyde. Aldehydes and ketones have the same core chemistry. If sodium borohydride reacts with our ketone, guess what our sodium borohydride is going to do with the aldehyde? Same thing, and going to react it across. So what's special about our new functional group, our polar pi bond with a leaving group, is that it now has the ability to react twice. I don't get it just stalling at one stop. I have to recognize that it continues to react. Right? Which means we could potentially add some information. Right? Add some information back towards this thing. You'll note within this we do not have our aldehydes or ketones. Why not? They don't have leaving groups. This is really just showing our leaving groups. Okay? But what we could do is insert the aldehyde and ketone into this to represent where they show up as far as reactivity. And where are they? They're right in here. So that if I go through and I reduce an ester, the ester reduces to the aldehyde or ketone, that's higher in energy than it. So what happens? It reacts again. So if I know the chemistry for my aldehydes and ketones, I can now start to predict what's going to happen when I run those same reagents again with these complex functional groups. Kind of, sort of? If you're not feeling overwhelmed, for the record, you're doing something wrong. Okay? Talks about the difference there in that video, which is useful, but again, a bit over the top for what I wanted. Do not dye ball. Damn. I didn't think that was in that video. Don't worry about dye ball and this other thing. All I want is sodium borohydride and lithium aluminum hydride. Okay? Knowing their reactivities becomes important, and the differences in reactivity we actually already talked about at the last reference, which then aligns us quite overwhelmingly at electrophile aromatic substitution. Do you want to talk about yet another new reaction? Okay, I'll give you a 3-minute break. Okay, on Thursday we will go through and talk through it. I would argue EAS is a little bit more straightforward. Okay, it's really just resonance in dealing with those kind of core functional groups, okay, or core reactivities. So we'll set you up with a clear electrophile and then the aromatic ring, react. Okay, we won't push the exceptions too much at you. Of course there's limitations in this one. But this one does cover all the reagents that you would see. And I will try on Thursday to backtrack through and delete stuff from it. EAS to me, I know I said we'd stop. I'm not talking about chemistry, I'm just talking about logistics. EAS I think is the least important of all the reactions to deal with because it's not biochemically relevant, and I don't think anybody here was doing anything that was outside the realm of biology. Since we're all fitting within that category, EAS becomes not super good. Not good, not useful. Okay, so it's not a huge one to stress about. What I will go through and do on Thursday is delete some of those reagents out so that we don't have to worry about all of the reagents within it like we've been doing with the past ones. As you saw, there's not a whole lot to talk through. I'll talk through the generic mechanism, and we can talk about some substitution kind of chemistry within it, but then I would bet we'll be done plenty early on Thursday, and that's where we should really be opening it up to whatever questions you've got, and we will stop with content delivery. Kind of, sort of?
Yep.
Okay. If you got questions, you can come up and ask. Otherwise, we'll see you Thursday. Sorry, I know. Did I talk about Friday or Monday at all yet? No. This Friday, 10 to 4, and Monday from 9 to 5, I will be in the Pecos Tutoring Center for those entire time ranges. So if you've got questions, you can come get help from me there to encourage participation or attendance. I will also be supplying pizza, usually copious, ridiculous amounts, because I expect more people to show up, and nobody ever does. But that's okay.
How does that work if you don't have a parking pass there?
You don't need a parking pass at Pecos. Pecos doesn't have the same issues. The only reason you need it here is because of ASU.